we can now write that particular combination of values as a particular sum. We now have essentially the convolution sum that is valid for discrete time systems. We have our discrete time convolution sum, which is this y of n is equal to the sum from L equals 0 to n of h of L x of n minus L. And that will actually produce these pieces that we just had before. For example, if we wanted to look at the output y at time 0, then we would be looking at this sum from L equals 0 up to n, which is 0. This is now h of L x of 0 minus L. But in this particular case, L is 0, and so we have h of 0, x of 0, which is what we had just computed. If we look at another one, let's say we did y of 3 at n equals 3. That's now going to be this sum from L equals 0 to n equals 3, h of L x of 3 minus L, such that if we now look at the pieces that create y at time 3, we now have h of 0, x of 3 minus 0, or x of 3, plus h of 1, x of 2, which is 3 minus 1. Then we have h of 2, which is L equal 2, x of 3 minus 2, which is 1, plus, for L equal 3, h of 3, x of 3 minus 3, which is 0. And that indeed is the combination of values that create x at time n equals 3. You can see then that we now have, I hope, motivated this expression for the convolution sum. This y of n from L, this sum from L equals 0 up to n of h of L x of n minus L. If you look at this algebraically, you could actually write this with the arguments of the pulse response h and the input response x interchanged, meaning this is equivalent to looking at this sum from L equals 0 to n of h of n minus L x of L. And in the limit, let's say that we look at the limiting case on the first one. We see that now instead of n we're dealing with continuous time t. This sum becomes an integral, and now we're integrating from 0 to infinity of our pulse response, our impulse response, over the variable of integration, which we've called tau, x of t minus tau d tau. That's now the convolution integral, which is valid for t between minus infinity and infinity. And I hope that particular discussion, or this particular discussion, is helped motivate this governing convolution integral, which the convolution integral likewise can have the argument of the impulse response and the input interchanged. We could now say that that's this integral. In general, it's minus infinity to infinity h of t minus tau x of tau d tau. Which of these integrals you use is really going to be dependent on which particular waveform, the impulse response or the input, is easier to flip across the vertical axis at time 0 and then slide it around from t equal minus infinity up to plus infinity. That, I hope, motivates this convolution integral.